So we can go on,
Yes,
and um, next is David Carfi. So here you
yes,
are.
yes.
So you're going to talk about geometric and algebraic topological structures in Schwartz distribution spaces for relativistic quantum mechanics. It seems a
Yes.
very challenging talk.
Yes. And more challenging, I have decided to construct my talk at Blackboard with the Blackboard. So now I'm switching off my camera in order to write down my talk on Blackboard. So sorry, and I hope it is not too much annoying. Did you see my screen? Yes.
Yes, it is
Oh,
a sort of blackboard. Yeah.
yeah, exactly, a blackboard. And I will construct my talk on a theory that I developed in the last 30 years. And just, well, the foundations of quantum mechanics, not in Hilbert spaces, but in distribution spaces. So the main characters of quantum mechanics are, first of all, the space of states, S. So we need some vectors, wave functions, representing our system. Then we need also the observables, which will be operators, linear continuous operators upon S. And well, let me change okay. First point. 0 point is the state space. The second point will be the evolution equation. Evolution equation. That essentially is the Schrödinger equation in its most general form. E hat psi equal H hat psi. I mean, the energy operator that I'm coming to define, applied to the wave function, to the state of the system, it should be equal to the Hamiltonian operator applied to the wave function. This is the second character, the second actor. Then we have the third important actor. In my state space, I need to superpose the states and superpose continuously and discretely. So I need to move in a space in which the continuous superpositions are allowed. For character, the basis. In quantum mechanics, we have the position basis, we have the momentum basis, and we have, for example, the number operator basis. So we have two very important continuous bases, and we have one discrete basis. So my space is so strange that I can generate the space by means of continuous bases and discrete ones. Clearly, Hilbert spaces cannot enjoy this property because Hilbert space could be separable, or not separable. If the space is separable, I have the discrete basis. If the space, Hilbert space, is not separable, I have, well, continuous basis or other kind of basis. In the state space of quantum mechanics, for one particle, the elementary one, I mean the simplest one, we have two kinds of possible bases, continuous and discrete basis. Then we have another structure, another algebraic topological structure, the Dirac product. I can calculate the product of an entire basis of states times one state. And for example, I have expressions like x, y equal delta x minus y, which means that if I calculate the product of the position basis by another eigenvalue, eigenvector of the position operator, I obtain a Dirac delta. How to obtain a Dirac delta from the product, this inner product of two objects? We will see. Another actor of our quantum theory is the spectral part. Spectral. So I need to decompose the operators as, combinations of projections, if you want. But in quantum mechanics, I need a continuous family of projections. For example, we have x. This is a possible projection, and x is a real number. So we have a family, a continuous family of projectors. And finally, I put the 7-point, the probabilities. So I shall show you that the best possible space to construct quantum mechanics is the space of temperate distribution. Well, first of all, at the beginning, in 1925, Schrödinger thought to its state space as the space of C infinity RC functions, complex functions defined upon R. Why C infinity functions, smooth functions? Because I need to calculate the derivative with respect to time, multiply IH bar, apply to my state, and then I need to apply another differential operator, the second derivative with respect to space. So I need to calculate the derivatives. And clearly, the most simple choice is the space of smooth functions. I have no problem in differentiating the functions. Moreover, the space C infinity RC is a very good space because it is a Fréchet space. I mean, it is a metrizable, the topological vector space. It is complete. It is reflexive. And it is a Montel space. Briefly, Fréchet space means topological vector space with topology generated by a metric. Complete means that any possible Cauchy sequence is converging. Reflexive means that if I consider the second dual of S, I obtain S itself. And Montel means that all compacts, subsets of C infinity are bounded and and closed and vice versa. So I have a very important property from the analogous to the Rn Euclidean space.
But David, sorry, David, may I ask you? The problem is that R is non-compact, so it is not a Fréchet space actually. You need compact of R because everything.
What space is not a Fréchet space?
C infinity RC. So how it is not met? It depends on the metric. Since
yes, obviously, absolutely. I consider the Schwartz topology on the C infinite space. The Schwartz topology is endowed with the Schwartz topology. This is a Fréchet space. And another, yes, absolutely. And another Fréchet space is the space S RC, the space of infinitely differentiable functions rapidly decreasing at infinity. You have two topologies, Schwartz topologies, that are generated by the numerable infinity of seminorms. And these two spaces, Schwartz spaces, are indeed Fresher spaces. You don't need the compactness. And moreover, because these two spaces are Montel spaces, if well, the only Montel spaces, finite dimensional Rn, in which the compacts are all and the closed and bounded subsets. So yes, if you consider, for example, L2RC, okay, this is not a Fresher space. This is a Hilbert space, and it is not a Montel space. So the closed and bounded subsets are not compact, okay? But in C infinity RC and SRC, all the bounded and closed subsets are indeed compact.
So may I ask you, maybe, so Fresher space is a space whose topology is defined by a infinite family of seminorms.
Yes, and exactly the numerable family of seminorms. So you have, one moment, so you have, this is for sure is a classic result. So you have C infinity RC, and the topology is defined by Pn, n belonging to Rn, and this family of seminorms generates a metric in the standard way. You know, sum n equal 1 infinity, 1 over 2n, etc., etc. And this is a Fresher space. Well, what is a Fresher space? A Fresher space is a topological vector space which is complete and metrizable, and complete with respect to the topology. I mean, the topology is generated by infinitely many seminorms, but the numerable family of seminorms, and it is metrizable in this way, defining, and very interesting, the bounded and closed subsets of C infinity with respect to this topology are compact. And I add more. If you consider, well, the standard symbol for this space is E. We use E in this case, and the dual, the topological dual of E is another Montel space. It is obviously not a Fresher space. It is a very huge space, this space. It is not a Fresher space.
Yeah, just a question. So to be sure, so you consider, say, infinite family of closed intervals, and in this sum which you write, you take. So when intervals go to infinity, you divide them by two to the corresponding power.
Yeah,
yes,
exactly. Yes.
So now I understand. Yes. So this covers compactness. So this instead of compact. So now I understand. Thank you very much. So that's all. I understand now. Thank you.
Okay, perfect. And so, and the very important features of the Montel spaces and Fresher spaces are that here, they are reflexive. They are reflexive, and here we can define the superpositions. As a matter of fact, is better to use S, the space of rapidly decreasing functions. It is equally a Fresher space. It is a Montel space. It's reflexive. It's complete. And another important property is that the Fourier transform is a topological isomorphism between S and itself, and F extended from S prime to S prime is a topological isomorphism. So we have two topological isomorphisms. This is very important, and I show you, coming back to the to the talk, why. So we have Schrödinger. for Schrödinger, psi should be C infinity R C. And the Schrödinger equation, classic Schrödinger equation, is IH bar d over dt psi equal minus h bar squared, well, 2m d squared dx. Okay, so if you substitute, we have a family of solutions, a very important family of solutions of this equation. Is the family beta? Well, beta equal beta. This is obviously not a denumerable family, but it is a continuous family. P E, with P and E belonging to R. Beta PE is exactly e to the, well, I over h bar px minus et. So if you substitute, well, insert this function here, you obtain an equality as soon as E is equal to 1/2 over 2m, if you want, d squared. So as soon as these two terms verify this equation, you obtain a solution of the Schrödinger equation. So we need these functions, beta PE, inside our state space. Clearly, E, the space E of the smooth functions, contains, well, any BPE. But S does not contain BPE because the module of BPE is equal to 1. They are bounded but not rapidly decreasing at infinity. So if we want to use S and S prime, we have to choose as state space of our system the space of temporal distributions. This space contains E and contains S. And by the way, S prime contains also L2. So we have a space sufficiently large to contain all the smooth functions, rapidly decreasing at infinity, and all the square integral ones functions. So we can coming back to our program, we have our S, which now is S prime, the space of temporal distributions, and here we have linear operators and homomorphisms. I mean, well, another important point, but well, the time is going. Another important point is that the differential operators, dt, dx, and so on, any combination, linear combinations of these operators, and also obviously dn over dxn, are all linear continuous operators. Well, this is another important point of the Frechet space and the dual of a Frechet space. So while in S2, these operators are not everywhere defined, and moreover, they are not continuous. On the space of temporal distributions, all these differential operators are linear and continuous. So the Schrödinger equation, the classic Schrödinger equation, well, I h bar dt and so on, well, a constant times d square psi over d x square. This is a linear and continuous equation, which is not in L2. It is not in L2. In L2, this equation is not everywhere defined and it is not continuous. So I cannot apply the operators to the superpositions, to series and so on. Well, in the few minutes left, I show you the definition, what kind of superposition we should use in S prime. What is this? The idea is to superpose a family of distributions, VI, I belonging to R, with respect to a temporal distribution, and obtain another temporal distribution. I will show immediately the fundamental example of quantum theory. In quantum theory, any state psi should be obtained, expanded, if you want, by itself times the position basis. What does it mean, this? The position basis, which is in our model the basis of all Dirac deltas, is an eigenbasis of the position operator. We consider the position operator X, which to psi associates the multiplication of X times psi, the coordinate X. So if you apply delta to delta X, you obtain this X times delta X. So delta X is an eigenvector of the linear continuous operator X, and the corresponding eigenvalue is exactly X. So if I can expand any temporal distribution in the space of states as a linear superposition, this is, if you want, an hyperlinear superposition because we need the integral, we have proved one of the main features of quantum mechanics. The states can be expanded in any eigenbasis of a linear continuous operator. And I will show this in 1 minute. What kind of definition is this? This definition is the Pettis integral, or if you want, the Bourbaki integral, or if you want, again, the Dumford integral. So the Dumford integral is defined as follows. I apply this superposition to a test function, and I should obtain a number. What number? Well, we consider psi and apply psi to V phi. What is this V phi? This is a weak integral. So this is a distribution. So I need here a test function. What is this test function? The test function V phi is simply the function associating to x the value of Vx upon phi. So if you use this definition and apply the delta family to phi, you obtain delta phi x equal delta x of phi, which is phi of x. But this implies immediately that the test function delta phi is nothing but phi itself. So when you continue this calculation, instead of V phi, you can put phi, and so you obtain psi of phi. In other terms, the superposition psi delta instead of V is equal to psi. And we have decomposed any temporal distribution in a superposition of the delta family. So as you see, in temporal distribution space, you can reproduce the superposition of infinitely many states and obtaining again a temporal distribution. Why is that possible? It's possible because the space S prime is complete with respect to its own topology. And so if you consider family of distributions which are Schwartz functions but Schwartz functions from R to the space of states, then you can always integrate and obtain a temporal distribution. This is one of the main properties of the space of temporal distributions. I see that I almost finished my time.
Yes.
Yes. And I leave, if you want, some minutes for the questions instead of continuing.
Yes. So we tried to follow your chalk and talk exposition. It was difficult. I got that you somehow are trying to replace Hilbert space with another space.
Yeah. Yes, indeed. Because Hilbert space is not enough to represent not even the basic properties of quantum mechanics. And I want to underline in Hilbert space, you cannot have a basis of positions, because the basis of positions is a continuous basis, okay? So in Hilbert space, well, if the space is separable, you cannot have a continuous basis of the space, because any basis in a separable Hilbert space is discrete, is indexed by a discrete set of values, okay, by n. Then you can think that you can use non-separable Hilbert space, okay? But also in this case, for example, you can consider the position basis, okay? And you can generate span, the vector space generated by those objects, and then you can complete with respect to scalar product, okay? So you can obtain a kind of L2 delta. But when you go to expand one psi belonging to this new space, okay, you do not obtain an integral. No, you should use again the how to say, the series, okay? N belonging to, well, N belonging to R, but only a denumerable infinity of these coefficients could be different from zero, okay? Because this is the basic property, the basic definition of the linear combinations in Hilbert spaces. Okay, so, well, you cannot substitute the summations with integrals in Hilbert spaces. You cannot, even if the Hilbert space is non-separable. Because how to define the integral? You can define an integral in a feasible, reasonable way. In temporal distribution space, you have already your integral, which is the Pettis integral. This is the Pettis integral. This is the definition of Pettis integral. Pettis.
Okay. It is the SS prime space you defined before.
Yeah, obviously
Listen,
you
David,
have to change
we don't have so much time to
to discuss. I know.
Sum up your 15-year of studies.
30 years.
50,
30
years. Okay. So maybe it is something interesting, maybe it is something original. You must keep in your mind that Hilbert space, we all know the limitation of Hilbert space, but it is considered the best space for quantum representation. So your claim is very strong. Are you supporting it with further studies with other?
Yeah. Well, indeed, the idea is not completely new, but in another spirit. I follow the observations of, Zeidler, Zeidler is a Deutsch mathematician, and Zeidler recognized that Hilbert spaces cannot represent the bracket notations, the bracket calculus, okay? So already in literature, more than 30 years ago, one great mathematician recognized this problem. And another one is Bohm.
Yes.
Bohm is quantum, yes, famous, very famous, and his pupil Gadeia. And then where they used the triples, the Gelfand triples, sorry, this is S, and L2 S prime. So in some sense, they used both the Schwartz space of rapidly decreasing functions and the temporal distribution spaces. But they used these two spaces like, a kind of decoration of the L2 space. In other terms, when I fail to find something here, I search for something here or here, okay? And they call this rigged Hilbert space. Hilbert space. So the theory of rigged Hilbert space already existed.
Okay.
But it is not so complete. For example, they do not define the superposition as a Pettis integral. They do not define the Dirac orthogonality.
So you feel that you have added something original and something strong in order to propose this new theory?
Yes, for example, one possible application is the definition and solution of the relativistic Schrödinger equation, m0 c squared plus p squared, and applied to psi equal IH bar d over dt. For example, this equation was impossible to even define because you have no fractional differential operators in Hilbert spaces.
Yes, but, in fact, Hilbert spaces is used for quantum mechanics and does not apply to relativistic field. Well, we wish you good luck.
Thank you. Yes, thank you.
Just don't be too focused on this idea to the level, I want to give you an advice, to the level of craziness. Because as the great physicist Enrico Fermi said, physics can be tricky because you follow a model that can be wonderful, but it doesn't work in nature. So your model seems reasonable, but if it doesn't work, just don't get crazy. Okay.
Oh, no. Okay, I will follow your suggestion. Thank you very much.
Thank you for your long explanation. Yeah. And
may I also ask you? Let me ask.
Yeah.
David, actually, I'm not sure that the space of C infinity function from R to C is. How do you correctly define this topology?
How do you define the topology? Yes, well, essentially is the topology of uniform convergence on compact sets.
Yes, but this is yes, I understand this, but this is essentially this is another topology. This is like this is another kind of topology. So I'm sorry that it is maybe not metrizable because of non-compactness. So it is comparable with so-called strong C infinity topology on the space of functions. So it is not. So if you the problem is that if you for any kind of norms which you put on your functions, you can find a function which on infinity which increases essentially faster than any norm. You can also find this function, and so this norm.
Yes, but yes, okay, but you have this kind of well. Let me remember. So Pn yes, is a kind of supremum, okay, on X belonging to a Kn, a compact of, well, put psi of X, okay. And, well, you also have to use the derivatives, okay. And so you work always on a compactum. And the union n equal 1 to infinity of all these compact sets is indeed R, okay? So you decompose R as a union of compact sets.
So maybe may I ask you, so your norm, so you have actually family norms depending on the degree of the derivative and compact set, or you take supremum over all?
No, you need the sum over well, m equal 1 to infinity.
Well, but here, yes, but here you may have a problem because some functions may have infinite norm. You can find some function which increases very rapidly on infinity.
Yes, but you are working on a compact.
Yes, but if you cover and in any way you can always.
Well, okay, not infinity. Okay, but you obviously the topology is not mine. The topology is Schwartz, Dieudonné, and so on. So it's a very classic topological.
No, but this is no okay, but. This norm is, so you can find, if you fix any family of compacts, you can find a function whose norm, which is written here, will be infinite. This sum can be, you can always find the function for which this norm will be infinite.
You use, well, trunk your function, your sum at, I don't know, alpha, and then consider alpha belonging to, well, n, for example. So you obtain again a denumerable set of semi-norms, and are always finite.
I'm not sure that you can. Okay, maybe, but this is comparable with C-infinity topology on the spaces of functions, and actually,
yeah.
And it is known that that space does not satisfy. It is not local. Has no local basis at points. So this means that it is not metrizable at all.
No, C infinity.
Yes, R to any. Yes, if R, or instead of R, you can take arbitrary non-compact manifold. And if you handle this,
obviously,
infinity topology, it is not first countable. So therefore, it is
yeah. Obviously, the properties of R are fundamental here to obtain finite numbers.
Yes. And in order, you need either to put some restrict, for instance, Schwartz space. This is the space of rapidly decreasing functions. So in any way, they take this only subset. So in general, this is actually maybe I don't know how this works in your construction.
Well, I will send you the family of semi-norms.
Yes,
I repeat. It is not this topology. This topology is a standard topology.
Okay.
Yeah. So
okay. But so if you just rely on this, so maybe there are some. Okay, let me.
Yes, we will discuss by email.
Sorry.
No. You are welcome. I'm very happy of your remote. Thank you very much. Thank you, Enzo.
Great. It is a very high level discussions about topology.
Yeah. I will send you the other materials. Thank you, David. It was very, very interesting.